tasks. We will discuss what is an image. Then we will talk about CNN architecture and its implementation in the source code. Let's start from computer vision tasks. And first task, and the most typical one, the most popular ones, and the ones that you most likely will meet in your professional career are the following: classification, object detection, and segmentation. They are quite simple, classical, and let's talk about them. Assume you have an image, and on image you have some objects. In classification, you will get one label per one image. You will say that there is a dog with some probability, as you see below. It doesn't say how many dogs are there. It doesn't say where is it. It doesn't say what's the area of the image covered with the dog. Classification actually doesn't give us any of that. Hence, we have object detection task. Object detection task gives us more information. Object detection gives us first class. It says, hey, there is a dog. Also, it says that there are two objects on this image. It gives us probability of each object to be in the image, but also it gives us a coordinates of the object. More specifically, not the coordinates of the object itself, but rather a bounding box drawn around each of the objects. You see coordinates here: x, y, y, y0, x0, y0 are the coordinates of the top left point, and x1, y1 are the coordinates of the bottom right point. Using these 2 points and knowing that it's a rectangle, you can calculate everything else. You can calculate height, width, etc., etc. Then you can crop these objects, whatever. Segmentation is even more enhanced approach. As you see, your dogs are encircled with highlighted boundaries, see? And let's talk about segmentation in a little bit more details, because there are at least 3 types of segmentation. A simplest kind of segmentation is semantic segmentation. Semantic segmentation assigns a class for each pixel within this image, including background. You can see here different colors, and most likely these are cars, and this is the car also, and they have the same color, right? Do we differentiate between instances? Do we know how many cars are there? No. We just know that this area of an image covered with class car. Same with people. You can see people here in red. Same with the road. You see the road in purple, but we don't know where each of the instances of people and cars are located. We don't know neither locations, we don't know amount, we just know for every pixel which class it covers. Then instance segmentation. Pay attention to the image C. What you can see here, you can see objects in rectangles. Something similar, right? Looks like a mix of a segmentation and object detection. And you'll be right. Instance segmentation, you not only will know the area, where is the area covered with the object, but you will also see that, okay, this is a particular object. You will be able to find out the coordinates of objects and say how many of this object you see on the image. The most advanced is panoptic segmentation. Actually, panoptic segmentation is a combination of semantic and instance segmentation. Here you can see cars, but they are in different colors. It means that we not only know that this part of image is a car, but we also know where each instance of the car are and how many instances of the car there are in image. Another task of computer vision is key point detection. As you see here, 2 major types of key point detection used for faces and for standing human key point detection. Why? Because it opens all the capabilities to pose estimation, activity recognition, and derivatives of these tasks like crime detection. So when you know activity and activity is malignant, you can also do performance analysis, like for sports and employment, like people in factory, they are performing well or they don't doing their job sufficiently, right? In sports, you can evaluate players, performance in football players, basketball players, and other things. And actually, it's used nowadays. For faces, key points allow us to find out the allocations of the important features of the face, and that opens capabilities for face recognition, emotion detection, like calculating gender, age, ethnicity, and as well as heartbeat rate. Of course, those are just the two examples of key point detection tasks. There are a lot more, and you always can create your own. Like nothing prevents you from annotating the data with key points in a structured way, and then training algorithm that detects key points and then build up on that anything you can imagine. There are image in painting tasks. Image in painting is a large class, but in general, and general idea is to is having the broken image, like a missing part, is in painting a missing part of an image. You can see here reconstructed parts of image, and you can see that it's a high quality of a reconstruction. So the algorithm in paints cropped area pretty much efficiently, having only the context around. Another task is image restoration. You have corrupted image. It may be corrupted due to various reasons, maybe image compression, like you see here, see the image lost its quality after like compressing to JPEG or other internet formats, or some parts are lost, or it's overlaid with some text or anything else. Another task is super resolution, and it is super important because it actually works for us many years and maybe even more decades. It works for satellite images. So as you see, this is a original image with a high quality where you have a man and part of the increased size of part of an image, as you see here, right? And then you have as a baseline method a bicubic approximation, right? So this is a true image, and then it was compressed to a lower resolution, right? And then a number of methods applied to reconstruct this high quality image. So to summarize, super resolution allows us to increase the image, places on image, like 4 times, 8 times, 12 times, sometimes 20 times with in painting, like it's not a real zoom in, but again, in painting image to make it look like it has a higher resolution. This technology applied to your images in your phones. Then we have the blurring. The blurring is also a related task to image in painting and super resolution. You can see here blurred image, and the goal is to produce high quality image, and hence the technology is called deblurring. Now let's talk what is an image. Before we talk about models, let's talk about the data. What do we have there? And the image is a very simple concept. Image is just a matrix or a tensor. If we read like image like this, we will show it. It looks like this, right? So why you have coordinates here, right? There measure pixels, height and width in pixels. And if we print this image, if we print its shape, we will see that this is an image of a size of 427 at 640, and the third dimension is 3, right? What the hell is 3, right? Nobody told us 3. Where is it? The 3 actually is what gives you capability to see images in color. So actually, this is not a plain image. This is a tensor with a height of around 400 pixels, width of around 600 pixels, and depth of 3. Depth of 3 means that there are 3 layers And just because it's colored, and you might already guess what kind of layers there are. There is a red, green, and blue layers. And the interplay of these layers, different brightness in each of the layers, give you this color that you see as plain image. This tensor of depth 3, you can see here, if we plot it as a NumPy array, you can see that there are 3 layers, and each of them consists of some numbers. And those numbers are brightness of pixels from 0, which is black, to 255, which is white. And we have brightness for each of the layers, each of the channels. Red channel, green channel, and blue channel. The brighter the channel, the more of its color you can see on its plane representation. So actually, image is a matrix. And if it's a matrix of numbers, we can work with it in the same way we work with other numbers. If we make our task simpler and represent a grayscale image, right? Now we don't have color. We have only white and black and shades between white and black. Now you have a plain 2D matrix which has only height and width. It doesn't have depth, filled with numbers from 0 to 255. It's defined by the size of the type of the data. It's 8 bits. That's why, hence this range of values. And here you see the code with which we plotted this piece of image. You can see that this color actually is represented by numbers. The numbers are reverted. So 0 looks like white, and larger the number, the darker the image. I think it's OpenCV inverts colors. Now, knowing the specifics of the data, let's talk about a specific kind of convolutional neural networks and how these networks work with this kind of data. To show you the big picture from the very beginning, I must tell you that first there are input, right? We just talked about input. And then we will talk about something that is called convolutions. You will see something what is called feature maps. Convolutions, feature maps, pooling, convolutions, feature maps, pooling, convolutions, feature maps, pooling, then flattening, and fully connected layer. Fully connected layer is what we learned on the previous lecture. It's a fully connected neural networks, like dense neural networks. They are at the end of the convolutional parts. Sometimes this initial convolutional layers is called feature extractor, because in essence, they just decompose this image to a set of features for each color level. And then having the features of image decomposed, these features are passed to dense layers. So the dense layers recombine features and then decide what the class is, or where the location, or which pixel to inbuild in Paint. To summarize, convolutional layer is the source code that performs convolution. It's a piece of code that performs convolution. Convolutions are element-wise matrix multiplication. So we take a piece of image and we take a convolution matrix and we multiply each number inside the convolution matrix to each number in image. Then we had some convolved version of our world. We got feature maps. If we move with this convolutional image through every piece of image, original one, we will have its convolved representation. Feature map is the result of stacking of multiple convolutions by multiple filters. And we repeat this operation several times until we decompose image to features. Now we will talk about all of that in more detail. First, convolutions. To the right, you can see its implementation in code. It should bring you clarity about the essence of these operations. So think about this image. Remember, I told you that we take some portion of its image and we element wisely multiply it by a convolution matrix. So this is a portion of image, and then we multiply it by something that is called convolutional filter or kernel. Numbers here are static, but don't be fooled, they are not static in reality, they are learned. So the numbers here are weights in the reality, And when you train the neural network, actually what you do is that you're fitting this convolutional. You're trying to put here the best numbers you can to minimize loss function. But what happens from a mathematical standpoint, you have a kernel with some number, and then you multiply each number to corresponding number in the input, right? So see, 0 multiplied by 0, 1 multiplied by 1, see, 2 multiplied by 3, 3 multiplied by 4, and then you just add up everything and you have some number. Now this number goes as a first convolved representation of your original input. What happens next? You move this convolutional frame one step to the right, and now you multiply 1, 2, 4, 5 for the same matrix. See, 0 multiplied per 1, 2 multiplied per 1, 4 multiplied per 2, 5 multiplied per 3. Next, everything adds up, the same as in previous case. And you put this number, the sum of the element-wise multiplications, you put as like to the next of the previous number. Now, if you generalize this, it looks like that you pick this convolutional window, you travel with it around all the image, right? And at every position, you sum up something and you put it as a one number of a feature map. You can see code here. You have some shape, then you travel through the shape 0 along the width of the image, and then in another form along the height of the image. And for every new element of the convolved representation, in our case output, you take the corresponding index element at corresponding index, you add up height, and you multiply it per k. And k is our convolution matrix. You take a slice here. This is a first index, this is a second index, matrix of 2 by 2. And then you sum up the sums of multiplication of products, and then you have y. The y is this output, the feature map. It's a simplified representation, but it shows the concept. And then you repeat it multiple times until you have a flat representation of your picture. Why we're doing this? Because algorithms cannot work with image as it is. For this image, if I want to say, is it a robot or not, I first need to understand, does this image have all the features that are associated with a robot? Does it have hands, robot hands? Does it have buttons? Does it have eyes? Does it have like robotic legs? Does it have antenna? And all of that. And I will have these answers like yes or no in this small decomposed representation. So each of these small rectangles will contain one feature extracted from image. The convolutional layer performs convolution. Let's review this part in more detail. So you have this elementary multiplication. Remember here we reviewed one step of a multiplication for all the image and then summary, like how we get feature map. Now the whole convolution layer. So this is convolutional layer. This is something that you will use in your practice and homework. The convolutional layer starts from initiation of weights and biases. Convolutional matrix 2D is a set of parameters. Remember I told you that this kernel, don't be fooled, it's not a static numbers. They are weights that are learned during training your neural network. And this piece of code shows you how these parameters are set. So every kernel or convolutional matrix has weights. Inside the matrix, they are parameters. Let's see kernel size. And we start from random numbers. And then bias. Yeah? Bias is a mandatory attribute of every layer. In our case, kind of layer is our convolutional matrix. Here, this function is a one forward step of a convolution. It's a one elementary convolution when we go from image to its feature map. What happens is that we convolve this image to some compressed representation that is called feature map. Okay? And you saw this code. We just putting it in place. We say that it's a part of a convolutional layer. It's a full forward step. Okay? And what we are training here, we're training the content of this matrix. We first populate it with some random numbers, right? But we say that these are parameters, weights and biases, and we learn them during training. And the only one parameter is X. X is this input image. Input image is a matrix of numbers.
Yeah, the only question is that when you create the Y matrix in the core2D function, so we create torch zeros and there is X shape of 0 in example, minus H plus 1. Why exactly this number?
We're just creating a matrix that fits us in terms of size, of shape.
Yeah, but why is this shape? Why do we subtract H in example and add 1?
Because feature map's size is smaller than input size. See, we gradually decrease the size of feature map. See, and this is just a formula of how to recompute new feature map having particular input size. These are parameters because for every layer of feature maps, we will have to recompute it again. So they are parameterized. X is input to this layer, X minus height and width of a convolutional map, this one. H and W of a kernel, height of a kernel and width of a kernel. X shape 0 is height of an input image, and X shape 1 is a width of an input image. And we subtract from it kernel height and kernel width. Kernel typically is 3 by 3. Original inputs are thousands by thousands. So we are very gradually decrease the size. If you take 1,000 and subtract 3, it will be 997, right? Then we add 1. It will be 998. So the height of this convolved feature map will be 998. And the same width. If the original input will be 1,000 by 1,000. Not that much, right?
Yes.
And why it happens? Convolutional matrix skips 1 pixel from the left side and 1 pixel from the right side. If it shifts by 1 pixel. If it shifts by more, the formula here will be different. And you will have size of feature maps, much smaller ones. Convolutional layer. Here is explanation. What is X, right? X are color input. So you have layers like a red layer, green layer, and there are blue layer, not shown here. And you have a kernel, the shape of a kernel, number of layers, depth, must correspond to the depths of input. Otherwise, the convolution cannot happen. How it works in input, for example, you have 2 layers. 2 layers on image. In reality, it's usually 3. And then each of the layers, by the way, they have a unique weights and they have different weights. They are multiplied per corresponding layer in the manner I showed you at the beginning. See? So they multiply here, then they move, then they multiply here, then everything adds up. Then you have one number here, then you have one number there. Here, you sum up this kernel multiplied by this, plus that kernel results multiplication by that layer, and then you have a convolution. This multi-layered kernel is called a filter. How the depth of the feature map is defined. What defines how many layers I have after the convolution?
Maybe kernel size?
No, it's defined by the number of kernels. One kernel produces one feature map. If I want to have multiple feature maps, I need to have multiple kernels. And that's logical because one kernel is designed in a way that it extracts one type of features on image. For example, I can say that this kernel finds antenna. Is there an antenna on image? It doesn't do anything else. See antenna, I'm looking for antenna. Is antenna here? No. Antenna here? No. Antenna here? No. Antenna here? No. Okay. And then I created a whole feature map that says me where is antenna. It's a simplification, a significant simplification, but the idea is like that. This output is element-wise multiplication of all the kernels in the filter. Let's see, they added to the other kernel multiplications element-wise, and I have a sum. And this sum is written here. Exactly everything that you saw here is repeated, but for multiple color channels. For simplification, there are 2 of them, but you can have 3, 4, and more. And then each feature map becomes an input for another layer. So first, it plays a role of input, our initial image. Then I have convolution, all these matrices, multiplication, blah, blah, blah. Then for each filter, I have 1 feature map. So how many filters did I have here? Yes, I had 4 filters here. That's why I got 4 feature maps. And how many filters I had here?
5, right?
5. And here, more than 5. Okay.
More than 5.
But there is a number of filters and there is a depth of a filter. See, the depth of a filter here is 2 because in its input has a depth. Now tell me what is the depth of this filter?
3.
3, because it's a color image, correct. What is the depth of filters here?
4.
4, correct, because the feature map now becomes an input and the depth of feature map is 4. Hence, I need to have filters of depth 4 to be able to multiply these matrices just from a mathematical standpoint. And here, the depths of my filters are
5.
5, correct. How many filters do I have here? 12 filters. Each of these 12 filters have depth 5. Now you know how the convolutional neural network works. If you have input of depth 3 and you have 2 kernels, each of them has depth 3, and you multiply each of them per the input, you have a convolution with depth 2 because there were 2 filters. Now we have to review such concepts as padding and strides. Padding, preserve or increase size of output by artificially adding 1 or more surrounding pixels. If I have padding 1, it means that I added a layer of additional pixels with width 1. It is done to increase the importance of pixels on the sides of image, see? And now let's compare how many times my kernel will visit pixel number 0 and pixel number 4. So I visited pixel with value 4 times, and I visited pixel with number 0 1 time. It means that the importance of pixels on the sides of the image is severely decreased. It leads to that I will tend to miss information around the perimeter of image just because I visited it rarely. That's why we have padding. And this is a basic implementation of padding where each pixel is just filled with a 0. And you have options there. You can fill them with zeros. You can fill them with any number you want. You can mirror them. Mirror means like put 4 here or put 5 and 4 here. This is the numbers that are closest to this padded pixel, but in reverse order. You can set it as increase, so it will just copy it like 5, 5, 5. Whatever makes it better and disturbing the original results less, whatever option works better. Now, another concept is stride. Stride is how far you step with your convolution kernel. At the beginning, I told you that we travel by 1 pixel. We select our region of our input here, right? Then we move by 1 pixel to the right. So we will multiply our kernel by 0, 0, 1, and 0. After we did it, yeah, we will get 3. Then we move to the right for another pixel, and we will reside in 0, 0 to 1. We will do multiplication, addition, and we'll get 8, right? But we have an option to create larger steps. If we put stride 2, then we will step each time, not by the 1 pixel, but by 2 pixels. See, we multiplied all of that on this region. Then we moved to the right by 2 pixels at once, and we got 8. What happens? What's the impact on our results? See the size of a kernel. I had input 5 by 5, and with stride 2, I got output 2 by 2. Yeah, it decreased a lot. And in this case, I had stride 1, and I convolved input 3 by 3, and I got 2 by 2. Yeah, it's only slightly reduced in size, right? This is impact of stride. Stride makes your output smaller and makes your attention weaker, I would say. You tend to miss objects more. Stride was a nice tool in early ages of convolutional neural networks because it allowed people to have less layers. They allowed people to jump to smaller feature maps faster. So if I had stride 2, I will get from this input, not these feature maps, but these feature maps. And from these feature maps, directly these feature maps. Like I will skip 2 layers. Did you get it? Another concept that we have to talk about is pooling. There are 2 types of pooling, average pooling and max pooling. Average one is more rare and gives blurry pooled results. Max pooling is more used, and again, it's used for making your input more granular and smaller. See, pooling is very simple. It's non-parametric layer. There are no weights to learn. It's a simple argmax operation. If it's a kernel 2 by 2 of max pooling, and each zone, see, it's a red zone, yellow zone, green zone, blue zone. In each zone, its operation selects the largest number and puts the output. And notice that input, it decreased input twofold. So this output is 2 times smaller than the input. See? So for the red one, we select the largest number 20, we put it here. For the yellow one, we selected the largest number 30, we put it here. Same for blue, 112, put it here. For the green one, 37, put it in 37. See? Its implementation is very simple. Max pool, it has a 2D, 3D forms. It's a size, and again, this size is wrong. This one is 2 by 2, and here is 2 by 3. And also, you have a stride. Stride here also is 2 by 2. And summarizing all of that, you will get everything what I said. You will get convolutional neural networks in the form they've been there like almost 25 years ago. Right? At the times of Leonard 5, this is a neural network developed by Jan LeCun. Its exact architecture is in front of you. So you have input. This network cannot maintain larger inputs because there were no sufficient computational powers at that time. So it works with a small images, 28 by 28 pixels. This image is simplified because each side is 28. Then convolution, pooling, convolution, pooling, then flattening this last layer of convolutions to a dense layer, and then putting several dense layers, and then classification. See 10 neurons in the last layer. We classify this image to one of the 10 classes, and these classes are numbered. Yeah, we say, okay, this is 7, so your output will be 7, and we try to fit that. Questions?
Where do we set the number of kernels that will be in the layer in code? You said that the number of feature maps is corresponding to the number of our kernels. So where do we set that number of kernels? We only have kernel size, as I see.
Right, because this is manually implemented everything. It's in the parameters of the layer. Here, see, It's one of these numbers.
Okay.
Okay, so this is a full picture, and who will say how many filters are used here?
6.
6, correct. Because I got 6 layers, it means that I got 6 filters here. What was the depth of each filter?
1.
1, because it's a grayscale image. It was flat, right? Okay, you get it. I'm happy. Let's move on. This is all the layers with all the sizes for this convolutional network. See, the input is 28 by 28. Then you have convolution 5 by 5 as 6 convolutions with padding 2. Then you have average pooling with a kernel 2 by 2 and stride 2. The same as I showed you, but max pooling, it's average pooling. Yeah, as you might guess, average pooling just average all the numbers in its attention area. Then you have flattening, another set of convolutions and pooling. Then you flatten it to fully connected, and you have several layers of fully connected that recombines features, right? Here is its code, and you will work with it in your homework. See, it's 1 is number of image. It's a batch size. For simplicity, it's 1. Then 6 is a number of kernels. And then kernel size 5 it's a 5 by 5 matrix. See, 5 by 5 and 6 kernels and padding 2. And then you also give it an activation layer. So what kind of activation does it use? Right. Then you have average pooling 2D with kernel size and stride. And then you have another convolutional layers. So how many convolutional layers does this network have?
2.
2, right? So the pooling is just addition to convolution. You will also see other modifiers of convolution, like normalization and other things. Then pay attention to this layer flatten. Flatten is how we move from feature extractor convolutional layers to dense layers. See, dense layers are called linear and activation sigmoid for neurons, right? Okay. Do you have any questions?
Can you explain why on the fifth line we have input size for linear? In the sequential first linear. First linear layer, we have input size 16 times 5 times 5. Why this number?
Because there is formula to calculate it. And for linear, you have this is the only hard place here, right? Because you need to calculate this number. But it's easy to calculate. See, it's 16. It's number of output filters. Number of filters to convolve this image representation here. This convolution map. So I got this, right?
Yes. But why we multiply
I got this,
it?
and then I got 16 convolution maps. And then I have a number of convolutional filters. Then I multiplied by kernel size this and kernel size this, and I got number of the first dense layer. This.
Okay, thanks.
This is output. but its input will be, give me a second. $400. Input size will be 400. After flattening,
Can you please explain why sigmoid activation function was chosen for this neural network? Is it
because
important?
this guy lived in the time where it was fancy.
Oh, okay.
You can put wherever you like there. If you prove that it works better, yeah, you can blame him in selecting weak architecture. But I don't think he's too famous. And it's too late. I hope you get it, right? This is just something that he selected for his architecture, and he gave this architecture his name. So at the time, it was a big thing. Now, of course, it's unusable, and you have much more powerful architectures. But this is a good example to explain you the architecture itself and how it works and all the major components, because frankly speaking, they didn't change at all since then, like at all. All these pieces are there. There are just more and more and more of them. And the intelligence that you can hear about nowadays is just created with a large number of these components. That's it. The more neurons, the more convolutions you have, the smarter the networks becomes, and more and harder tasks it can handle. Okay.
Yeah, sure. And another question I have. I heard that convolutional neural networks could be used could be applied not to just images, but to other tasks as well, other types of data. Can you please
Elaborate on that? Oh, yes, of course. So convolution is just a principle. It just works for images. It just worked for images probably initially. And another good example of application of convolutional networks could be anything that you can find a pattern of convolution. So when you take, so it looks for some patterns within a small chunk of data. If we consider, for example, time series, right? And there is some particular pattern of events within a small block of events, you can turn this thing layer to convolutional 1D, because now you have not a spatial data, but you have a time series, and you want to find these patterns with a one dimension. You can convolve one dimension, right, to something, and if there are patterns, this network will spot them.
Okay.
So another example can be time series, and they are applied in reality, and it worked at some point and gave good results.
So is it does it work better than LSTM for time series, or worse?
Yes.
Or better?
If you combine 1D CNN with the LSTM and with dense neural network at the end, you will get one of the papers that was very popular like 5-6 years ago. It was a breakthrough in the industry.
Okay, thank you.
Other questions?
I want to clarify that when our kernel have depths more than one, and on the last our layer of convolution or our pool layer, we have like three features, not a feature map of depth 3. How then do we flatten it to feed it to linear layer? We just summarize all the numbers.
You just take it and slice it like here are here's
Or
a
we
matrix
just
2 by 2.
multiplies them.
No, you slice one, you slice second, you slice third, you slice first, and you just put them in line, and that's it. And did you get it?
Can you please revert to the previous slide that is before this one? Before this one. No, not this is the next slide. Previous before that, there was a schema with previous. One more. And one more. I don't remember actually where. And one more. There was an schema with. This one. That was that. You see this? No. Next. There was a green, not square but rectangle, and in this rectangle, I see that we have two our kernels depth 2. Yes. Depth 1 is upper, depth 2 is lower. We multiply each for each our
By
color
corresponding
channel,
layer of a
color
kernel,
channel.
yes.
And we just sum it.
Yes, we sum everything as see it shown here. And we get one number, and we get one output feature map. That's why I was asking what is the size of this and how many are these, because this what decides how many you will have and what's the size. Or every convolution operation will give you one flat output. One.
So after this convolution, we'll have the feature map of depth 1. Yes?
One kernel, one output layer. I'm trying to say that if you see here 6 layers, then it means that there were 6 convolution kernels.
Yeah, I
It's
get
not
it.
shown here.
The number
If you
of
see
feature map-
16 here, it means that this 6 was convolved with 16 different kernels. It means it were 16 operations like this, and you got 16 flat outputs, and here you just put them together.
Okay. The question is, we have 16 kernels, new kernels to get through the convolution, and we apply each this kernel to all the 6 input
No.
feature maps. No.
No. Each of these 16 kernels will have depth of 6.
Okay.
Your input here will be of depth 6, and hence your kernel has to be of depth 6. And then you will have here not 2 but 6 here and 6 here, but you will have one output because all of them will be summed up to one number. No?
No, I think I get it. So the depth is the number of feature maps that we had on the previous layer, and the number of our kernels is that the number of feature maps that we get on the output.
Right. Yes,
Okay.
the number of kernels, you decide number of kernels. How people get these numbers, like why I have 6 here and 16 here? Because like this guy sat in his lab, for a few months and tried like 3, 6, 12, 10 here, right? Like 1, 2, 5, 20, 30. And he found out that for these numbers, his network just works best. That's it. There is no magic behind. I described you a brute force way, but please don't use it. There are Gaussian optimization methods. Please use them. They will decrease number of iterations to find your optimal architecture. Other questions?
Can you please repeat one more time what is padding?
Padding is adding extra pixels throughout the perimeter of image to make border neurons, pixels, more important, more represented in your output.
And this border is usually filled with zeros, or it depends?
No, it depends on the way you choose to fulfill them. There are mirroring, there are default. This is a default padding. It's stupid. It's erroneous because it creates a new feature in the place where there is no new feature here. See how this kernel reacts? It just detects borders. It detects where white color turns to black color. See? And with this padding, they artificially created such a feature, while there is no such a feature. That's why you need to use more advanced padding, like mirroring, or just copying the last value. So you don't create artificial borders, artificial features. It was a little bit advanced, right? But did I answer your question?
Okay, I see. And another question: can you please move to previous page with the kernel matrix, and where's adding and multiplication operations? Previous, please. Previous. Yes. Okay. So we can assume that this input data and the kernel data is our weights.
No, weights are inside within the kernel. 0, 1, 2, 3, 1, 2, 3. These are trained numbers. Again, don't be fooled. This is something that people put there. But when you will train network, you will have here W1, W2, W3, W4, W1, W5, W6, W7, W8. Weights to be learned. See parameter. They are parameter. See parameter. Self.weight is these weights. Set of weights.
Yeah, okay, and we multiplied it with the input data.
Right,
And
we have some start, see torch rand, it just gives them some random numbers between 0 and 10. No, I'm sorry, within the how torch.rand works, you give it kernel size is, it's wrong. If it's 4, then its matrix will be populated with random numbers, including 0, 1, 2, and 3. And it's a random population, but they are parameters. So they are aimed to be learned. And this is just initial guess. Remember, when we talked about dense neural networks, we said that we first populate all the weights with a small random numbers, between 0 and 1, and then we train the network until the loss function is as close to the 0 as satisfies our condition. Same happens here. Those are just start numbers, but then you train it. And how you train it? You say, hey, this is a 7. Yeah, and your output will be a 7. And the other image will be 8, and your output will be 8. And you will force weights within your convolution matrix here to be some numbers that extract such features that allow this network to guess correctly. And then you hope that for the new numbers it will work. Okay, did I answer the question?
the question is, can you please turn back to previous page one? We have a conversation. Yeah. So after this multiplication and adding operations, I cannot see any bias. Where is it?
It's not shown here.
but it is yeah.
Right.
Mhm.
Yes, you will have this thing plus B. Yeah, because if the bias shown here, that will raise even more questions and we will stop here. So it's just a simplification of a situation. But yes, bias is there. You can see it here.
Got you. Thank you.
That's another parameter. It's learned separately. Okay, thank you for questions. Any more questions?
Oh, yes, well, I have a question. In one of schemes of architecture, there were convolutional layers and pooling layers. Is there some general idea whether we should, at a certain point, add convolutional layer or just pool, or it's experimental and lucky guess?
If you have weaker hardware, then you use more pooling. If you have a powerful hardware, and you don't use pooling, that's it.
Okay, thank you.
Pooling allows you to have less weights and smaller model, less training time, lower requirements for hardware. That's it.
Okay, one more question.
Yes, go on.
Kernel is always a squared matrix, or it can be different shapes?
It can be anything you program, but the practice shows that the best kernels that work are 3x3, and they are used in about 80, maybe 90% of cases. The non-square ones are very exotic. I haven't seen them in practice at all because they create asymmetric feature maps, and then it becomes harder and harder to detect anything there because they're improportional and they skew the object representation.
Okay,
First.
thank you.
Second, they're almost always are odd numbers. I mean, they are not divided by 2. So this is wrong also. It's 2x2, but it's wrong. It's in majority of the cases, it is 3x3. Larger matrices allow you to detect more coarse-grained features on image. By the way, one of the Google architectures, Google Inception, it combines 1D convolution and different shapes, sizes of kernels, like 1x1, 3x3, 5x5, 7x7. The larger the kernel, the faster decreases the size of image. But the more coarse-grained features they detect at every layer. To put it in some reality, like small kernel will, struggle to detect a button. A larger feature will say, hey, there is a head. And the smaller one will be able to detect a button. That's an oversimplification. Okay, any more questions?
And the small kernel would be hard to detect the head?
The smaller the kernel, the more layers you will need to detect large objects on image. So the small kernel will not see the head. The small kernel will see some angles here, the corners, and part of an eye. It will not see head at all because it cannot digest it. From the first iteration, it will need several layers to detect it. Several cascades of convolutions and feature maps, like convolution, then you convolve it again, then you convolve it again, then you detect something.
Object detection task and, for example, classification task differs only in the in how the model gives the output. Yes, so convolutions are all the same.
Yes, yeah, you guessed it completely right. So it's only differs in the final layer. So is it the output? Is it the one neuron? Is it the several neurons? For segmentation, your output will be a whole image. See, because every pixel in this image is a target. Because for every pixel, you must say to which class it corresponds.
So it's just a big matrix, yeah? Matrix.
Yes. So your output will be of a size of this image. Let's say 1000 by 1000. So here you will have your output will be like this. 1000
okay.
by 1000. See? So for segmentation, it's a wrong. Yeah, it's a wrong architecture for segmentation. For segmentation, it's autoencoder type. It's fully convolutional autoencoder. So you will have convolutions, then some dense here, and then you will have up convolutions. Like you want to get back to this layer, but with labels. Deconvolutions.
Thanks.
Okay, thank you guys for visiting the lecture.